Good morning. I'm trying the geofencing version of iClicker Reef, so it's going to ask to use your location, just to see if it is a pain or if we're able to do it without trouble. If it's no trouble, we'll keep it. If not, then I'll try turning it off. I'm not sure if I can do it in the middle of the session, so let me know if you have issues as I'm walking around. I can help you try to get logged in, which I think is what Love is doing over there. Maybe something else? All right. So last time we were working on Chem Activity 34 in this packet. We got to a certain point, then we ran out of time. Surprise. So what I want to do now is, I think we finished Critical Thinking Question 10, and we did not start Model 4. So let's go ahead and start Model 4. I want you to go ahead and read the information of Model 4, and then try to answer Question 11. And this is Critical Thinking Question 11. So I'm going to use CTQ for Critical Thinking Question. And we're going to kind of go through. Some of these we're going to click in our answers and discuss. Other ones we're just going to shout out. So let's try to roll a decent pace. Our goal is by the end of today we will complete this packet, Activity 35 as well. For those of you who just came in, yes, you will need to allow location services on the app.
What if it didn't ask?
Then you might have already done it for a previous class or a previous
You probably
time.
have where your location is available for anything.
Oh, okay.
So the government's tracking you.
Yeah, aren't you worried? No, don't worry, somehow. Wait.
You must have been at this. I think I have like 2 extra copies of the worksheet, the packet. Does anyone forget theirs today or does not have it? Okay, did anyone not have it? Or you guys just forgot it? Not an acceptable excuse. Alright, so if you don't have one today, raise your hand. I think Logan, Trey. Anybody else?
No, I'm good. I'm not sure. I got mine.
Yeah, well, I mean, I have 2 copies, so.
I just got a hand up right now.
Wait, did you do that Wednesday as well? Okay.
Yeah, he did.
Like you have 3 copies now.
Yeah. I don't think that's but it's not what we want. But it will be good.
Taylor, do you have your packet? Great. Alright, so you guys are working on Critical Thinking Question 11 in Model 4 for those who just arrived. Make sure to read Model 4, answer questions 11 and 12. And if you notice, it is short answer, not numeric. That means you can add letters if that's appropriate. All right, let's do about 45 more seconds to answer CTQ 11. Obviously, keep working forward if you complete that. All right. Most people have been able to submit an answer. We only have 35 people today. Our numbers are dwindling. Stay strong. Keep attending. 35. All right, I'm going to go ahead and close this to see if we can actually look at its short answer, so it might be a total mess. It is a total mess. All right, looks like we have a mix, at least in our top 15 answers. Maybe that's not even true. Of 0 and of negative or positive 1662 kilojoules. What would the proper units be if we're talking about delta H of the process?
Kilojoules per mole.
Kilojoules for every mole. So we're thinking about, it's not how much energy, what's the change in energy if we burn gasoline?
How much do you have?
Yeah, it's really important to know exactly how much we have. If we don't talk about how much we have, we can't talk about the energy released or absorbed, okay? So our units are always going to be kilojoule for every mole of that reaction that goes. So then the question becomes, is it positive, is it negative, or is it 0? Talk to your neighbor, and I want you to figure out which one of those three you think it is. Positive 1662 kilojoules per mole, negative 1662 kilojoules per mole, or 0. I'll give you guys 45 seconds to discuss that, and then we're going to move. I'm going to hear from the group. All right. Can I hear from one group? What did you guys discuss? Which one do you think and why? Logan.
So we talked about a positive being 0 because the delta H from going from the one mole breaking it apart would be positive 1,662.09, but then going in reverse it would be negative, so it would cancel each other out.
So what you're pointing out is that there's something not included in this diagram, but it's in the question. And so if you if you reform methane from 1 carbon and 4 hydrogens, then that's going to release 1662.09 kilojoules for every 1 mole we combine. So the question is asking about both. It's asking about if we take this, we break it apart into its individual atoms, and then we recombine them. So that would be a difference of 0 kilojoules per mole. The bonds that we broke are just as strong as the bonds that we form. That means that there's a zero-sum change in energy. So I want us thinking about that. How strong are the bonds we're breaking? How weak are the bonds that we're breaking? What about the bonds that we're forming? How do they compare? In this case, they're the same. But as we go forward the rest of class today, and what you guys did in homework last night, maybe you didn't quite connect the concepts yet. We're going to do that in class today. So we want to think about how strong are those bonds, how much energy is absorbed or released when we break or form bonds. So go ahead and work on CTQ 12. And I'm going to have you guys click that in a second. So I'm going to go ahead and... Actually, let me just talk through what we're going to be doing today. So it's really important that we're thinking about what parts of a reaction require energy being input and what parts of it release energy. Endo and exothermic components, and that's the signage that Logan just talked about, the negative versus the positive delta H. This is what we're focusing on today, is calculating the change of enthalpy of a reaction at standard conditions. What are standard conditions again? Standard temperature, pressure. I believe that's what it's getting at. I'm 90% sure. I could be wrong. All right, and we're going to have a table. You guys picked up the table, right? That's the appendix from the back of the POGO book. Since you guys don't have the physical book, I printed out the appendices so we can use that. We'll use that a lot today in our references. We're going to be drawing enthalpy diagrams, like the one you just saw in Model 4, except we're not going to have the same reactant and product. We're going to be looking at what is the enthalpy of combination of our reactant versus product, what is the net change, And that's going to allow us to think about the relative strength of bonds. And we're going to do a lot of calculations around that as well. So question 12 gets at this last one. Based on a specific amount of reactant, what is the change in energy? So go ahead and do question 12A and B. And then I want you to click in your answer to 12B. Once you finish that, you can go ahead and work on exercises below that. I'll come around. Please raise your hand if you have any questions on how to do questions 12 A and B. Oh.
Yeah, I see it's just coming together.
All right, a couple more seconds. I think you guys know how to do this. I'm not quite sure where we're getting hung up. So one of the things I didn't see being done too much is people using the values we just talked about as conversion factors. For every 1 mole of methane torn apart into its individual gaseous atoms, it requires 1662.09 kilojoules of energy. That's a conversion factor. If we have 2 moles, we know how much. If we have 6 moles, we know how much. If we have 0.06 moles, we know how much energy is used or released. All right? So I want you showing that as a conversion factor. A question that Moab asked that was very pertinent is, we're not really used to seeing carbon as a gas and hydrogen as a gas. Are those stable? They're super unstable. So what this is saying is it's not talking about a logical chemical reaction, and I think it's really important to mention this. What this approach is saying is that if we were to come and find a methane molecule, how much energy would it take to rip it into all the individual atoms? Just tear them apart. They're not going to be stable like that. That's why it takes so much energy to do. And so for right now, we're just focusing on tearing apart these atoms. But what I want us starting to think about is if this is methane, and we tear it apart into the atoms, it's a conceptual step to say, well then, what are we going to form? And the bigger question is, what is over here? What is the product of this reaction? And then what's the change of each of these? And really, the logical part of this, the thing that actually makes sense, because these reactions happen, is we go from in this case, a more stable compound to a less stable compound. And the difference in energy of those two, that's where we're going to get to. This theoretical tearing apart into individual atoms doesn't happen, but it allows us to think about the energetics of relative stability of each other. Hopefully that'll become more clear as we go through class today. So if we look at this, how do we answer this question? Can I have someone explain to me how we use the unit conversions approach to answer this question? Aaron?
So we know that 1 mole of CH4 requires 1,662.09 kilojoules to break it apart. So to find the answer of 1.5 moles, I put 1.5 moles of CH4 over 1, and then multiplied it by the conversion factor of 1,662.09 kilojoules of CH4 over 1.
Great. So by using this as a conversion factor, if we know how many moles we have, we know how much energy is absorbed in this case. And one of the things I think that Love pointed out is that the terminology here, where did it say that? For 12.8, calculate the amount of energy released, always a positive number. What they're saying is if I say released or absorbed, you don't need the sign, because that tells you the sign. So if I say how much energy is absorbed, you just give me a number. If I ask how much energy is absorbed, it's just a number. The absorbed versus released, that already specifies whether it's a negative or a positive. If I ask for delta H, that's different. Delta H has to be negative or positive because that's telling you whether it's released or absorbed. So in this case, I had a question about, well, what do we do with 6 moles of hydrogen? This value that we talked about, the delta H of tearing apart 1 mole of methane, is the same for 4 moles of hydrogen being formed. So when we get a value of delta H, it's really specifically for 1 mole of whatever that thing is that we're looking at. In this case, it's 1 mole of CH4, which entails 4 moles of hydrogen. And so with this one, because it's 1.5 moles of methane, that means it's going to generate 1.5 moles of carbon and 6 moles of hydrogen. So it's just 1.5 times what we were using before. So what numerically did we find for this?
2,000.
Exactly?
2,493. It's 1
Point. All right, kilojoules is super important. How many sig figs is it? We have 1.5 moles. So that is, it depends on how they measured it or what they want. If we're assuming that someone measured 1.5 moles, then that would be 2 sig figs, which would mean it would be 2.5 times 10 to the third kilojoules. If this was the Yeah, I think I would go with 2 sig figs on this one.
Why aren't we putting the signs?
So this one is saying how much. Oh, so this one is asking what is the change in enthalpy. So we'd have to put a sign.
Oh, okay.
So is that a negative or a positive? When these things combine, so delta H. If it was saying how much energy is released, there would be no sign.
Wait, so why is that again?
So if I'm already telling you energy is being released, that's telling you that delta H is negative.
Oh, okay.
So then you're saying, well, this is how big the change is of release.
Okay.
Versus if I'm saying what's delta H, then you need the sign because it's released.
So if you don't want to do it, it's not a turn it off?
It would not be the most accurate answer, correct?
Okay.
For 12A, we just use one sig fig.
So 12A, what does it say?
It's the same thing, but with just 2 moles of CH4.
Yeah, so it depends on if they were meaning exactly 2 moles. 1 sig fig would not be inappropriate. I think in this setup, it would probably be better just to include more sig figs. I hate sig figs because they can get so picky. And the big thing is if I saw an exam that you actually wrote out the actual numeric answer that you got, and then said based on that 2 moles, it should be 1 sig fig, and then you wrote that below, that would be the best of both worlds, because then you said, well, according to sig figs, it should be this, but I want to make sure I include as much information as I can. Does that make sense? All right. So go ahead and work on exercises 3, 4, and 5.
Do you have an extra worksheet?
I do not. I've ran out of worksheets. So think about 2 more minutes to do exercises 3, 4, 5. If you finish, keep going on to the next pages even.
Because negative 6 or 716 is less than negative 714. I don't know.
Raise your hand if you have any questions as we're doing this. Don't want anyone sitting idle today. If you get stuck, please call me over.
Okay, so maybe it's graphite, and then.
All right, 30 more seconds. 3, 4, 5.
3, 4, 5 or 3, 4, 6?
Oh, 3, 4, 5. Because I wrote this when I didn't print out the appendix. I was not going to use the appendix, and I realized for 35 we need the appendix, so I printed it out. All right, let's talk through exercise 3. Go ahead and let's do fingers. 1, 2, 3, or 4. Because I don't have a clicker question for this. Which one of these do you think is obviously incorrect? Do 1, 2, 3, 4 for A, B, C, D, or none of them for 4? See a lot of 3s, a few 1s, and then some others. Why is 3 obviously wrong? Can I hear from a new voice? Go ahead, Josh.
The chart said so.
Okay. Besides the chart saying so, logic without using the chart. Why? Avery.
Or it should be negative.
Why?
Because it has to do with the amount of energy that's required when you create the bonds. You have to have the negative.
Okay. Can we have someone else say it in their own words as well? Kayla?
Is it because it's I2 is bonded to itself?
Okay, so it is partially, love?
It's a diatomic molecule. It's a diatomic molecule. Basically, it requires to be bonded to itself in order to maintain a zero entropy.
Not quite.
Are you confident to say since it's a combination, it's supposed to be a negative number?
Absolutely. So all of the individual atoms are defined, if they're by themselves, or that's our definition of 0 with this set of materials that we have. Your homework might define 0 as certain molecules, okay? Whatever atmosphere we're working in, it has to be where we define 0 as something. In this case, they define 0 as individual iodine atoms, right? Everything else that we've seen so far has been carbon atoms are 0, hydrogen atoms are 0. Everything an atom by himself is a gaseous form of 0. So in order for this to become I2, delta H has to be negative. That's what that question's getting at. All right, and then the value of it might be a little bit different from the table in the back. It shouldn't be, but I guess someone found there might be a little mistake in that. Okay. So the state is going to play a role in those values, and they might have mixed some of that stuff up. All right, so if we're looking at the big picture, and I didn't give you the table, you should be able to point out that if we're going from individual atoms at atomic combination, that we have a negative delta H because things combine. All right, and then let's talk about question number 4. Delta H atomic combination of graphite, negative 716 kilojoules per mole, versus diamond is negative 714 kilojoules per mole. On average, are the bonds stronger in diamond or graphite? What did you say, Christina?
I started out by saying graphite, but then you said on average, and I know you said, well, we're going to keep average of all the bonds, they're equally strong, I think. I might be wrong.
Okay, so why did you initially say graphite?
Because it releases more energy than diamond would.
So if we start with carbon in the gaseous state, 2 there, we're saying, well, how much energy is released in order to get to each of those? So this is delta H equals negative 716. Delta H equals negative 700 and that's backward tone. 14, 716. This one on the left then would be diamond. And this one here is graphite. So what does this tell us about the bond strength?
It takes more energy to make graphite than it does diamond.
Does it take more energy to make it? it releases more energy to form it. And this is asking about how strong the bonds are. So if it releases more energy to form it, based on our discussion over there, what can we say about how much energy to break it? The exact opposite, right? So it's going to require more energy to break carbon apart in graphite than it will to break them apart in diamond.
But that's not practical, right?
It's not logical.
Why is it not logical?
Against diamond, put it up against something, gotta break apart.
So we're thinking about the physical properties versus the atomic properties. And so graphite, if you look on your pencil, those graphite atoms are held very tightly to each other, but they're in sheets. And so between the different sheets, there's not very strong intermolecular forces because of the way that they're formed. Versus diamond, they're actually more intertwined, and those sheets don't come apart very easily. Not easily at all. It's one of the hardest substances we know. So that's where the difference comes. And it's great to include logic and no, that doesn't make sense. But sometimes we're thinking on the macro scale, we need to think on the atomic scale. All right, what about, based on their respective values, indicate whether the following statement is true or false. Explain your reasoning. Question 5. The bonds in tin tetrachloride are stronger than, silicon tetrachloride versus tin tetrachloride. What did you guys say? I hear true and false. Can I get someone to explain why? Angel? What did you say and why?
He said silicon tetrachloride because the number on the chart says 1629.3 kilojoules per mole.
16, sorry, what is it?
29.3.
15?
Oh.
15.9.
I just can't hear today. 1599.3 versus 10 is,
I was looking at the equivalent gas.
oh,
1260.2.
1260.2?
3.
Ooh. All right, so based off of that, which one has stronger bonds?
Oh, they were both negative, if that matters.
Absolutely matters. What's that, Savannah?
Nothing.
Which one's stronger?
The statement was true because silicon tetrachloride is strong.
So this one releases more energy when silicon and 4 chlorine atoms combine to form that molecule, which means it is harder to break apart, which means it has stronger bonds, whichever way you think about it. Stronger bond releases more energy when it forms, or you can say a stronger bond is one that requires more energy to pull apart. All right, question 6 then. Did you guys work on that yet? Go ahead and take 1 minute to work on question 6. It might help to draw the structure of them, the two molecules. Think about what does it actually mean. Maybe relate back to this diagram here. What are we talking about when we look at change in enthalpy of a reaction?
Maybe I wasn't
Like, to break up the...
If you finish this question, start working on activity 35. We got a lot left to do, and we got 14 minutes.
No pressure.
No pressure. Alright. Trey, can you tell me your little logic approach to this problem? When we draw out the molecules, I'm going to draw them out so you can actually picture what you're talking about, not just remember some formula.
Well, it's asking for the bond energy of the individual bonds. So since H2O has 2 bonds, and you get that total delta H value, you would just divide that by 2.
So we know that to break apart the entire molecule would require an input of 926.29 kilojoules for every mole. So that means that that comes from 2 bonds. We're talking about bonds forming and breaking. So that means that each one of these is a delta H. What did you find? 463 kilojoules for every mole of OH bonds that are broken. That's how much input of energy we need. What about over here? What is it for SH?
Can you explain why it would be negative?
Well, so I'm just talking about how much it would take to break them. So I'm not saying AC, but we can do that if you want. If we said AC, then that would be a negative number. Alright, so we're talking about that's the amount of energy released if we form an OH bond, released if we form an SH bond, or input to break those 2. So then which of those 2 is a stronger bond, and what's your rationale? Go ahead and talk to your neighbor, justify which is a stronger bond and why. Or do we need to do that discussion? Alright, so Logan, describe what it is.
Alright, so if you look at the diagrams, they have the same number of bonds, so they should be stronger, but the rationale between it is that oxygen, the bonds would be more electronegative, being closer to fluorine.
Careful, oxygen is more electronegative. The bond has a bigger difference in electronegativity, I think is what you were getting at.
Then so, yeah, so.
Alright, and so the rationale behind it you're getting at is that oxygen creates a little bit of a stronger bond. It also has to do with atomic radius, and we're going to get into that in a minute. Alright, any questions? Go ahead and get started on activity 35. You're going to have to use that table and the figure 1 there, and then we're going to start answering questions on that next page. We're going to try to do this now. We're going to try to speed this up a bit, so let's get moving. You guys like it when chemistry is super simple math and straightforward?
Yeah. Sounds like I'm an algebra.
That's too simple.
Well, I hope that you guys continue to think that thermochemistry is simple, because it really is. We just need to make sure we have the right frame of reference we're looking at, that's all.
We be provided with these numbers on the test,
Yeah, if I'm asking, I'm not going to ask you to memorize those values. You need to be able to use a table, correct? Ready, memorize, go. It's great, but for this.
Yeah, for this, it's not like that. Yeah, because now it's a pure movie. I just came out worse than like that. I'm so sure you know that.
No, I rechecked it, like, right here.
But it's not showing up on
It's not showing
this.
up in my phone.
Yeah.
So I'm thinking exponential technology, and
And then I want to take developmental knowledge.
well, yeah, I mean, I think I'm I'm just thinking, I don't know. I'm taking thinking that maybe sociology. I looked it up. I did 3 classes. I don't take it.
Yeah, you take development.
But what was exactly?
Dr. Chang is working on that conference right now. And Johns Hopkins requires 24 hours of anti-social even apply. That's a lot.
I've taken 3 or 4 of anthro.
Crazy, huh?
So is it endocrine or exocrine? Why is endo?
Because it's an overall positive number.
No, he just teaches all of them.
Alright. Let's have volunteers. I want to hear questions 1 through 5. I want to hear different voices. If you try these, please feel free to show your answer. Can I have a volunteer first for question 1? How much energy is required to break 1 mole of N2O4 gas, the reactant, into its gaseous atoms? Can we hear from different voices? Sarah.
1,932.93 kilojoules per mole.
1,932.93 kilojoules per mole. And so in this case, we wouldn't have to say per mole because it asks for 1 mole. Would you put a sign on that, positive or negative sign?
No.
So it's saying already how much energy is required. It's not asking for delta H. If it asks for delta H, you would need to put a sign to represent whether that's an input or an output of energy. All right, we know it's required, it's an input of energy. So what about question 2? Why is delta H not associated with the upward arrow, a positive number? How can we say that in a sentence? New voice, please. Ruby?
I said breaking bonds requires an input of energy.
Great. Breaking bonds requires an input of energy. That means that they are together because they're more stable together, because they fill each other's octet. I always want to go back to the quantum thinking about an atom. Stability is increased by forming bonds, so if it's in a bond, it's going to be more stable. Question number 3. How much energy is released when 2 moles of NO2 gas are formed from their gaseous atoms? Mohit.
1,875.73 kilojoules of energy is released.
Why is it not 937.86?
Because it's 2 moles.
Because in that diagram we can see that every 1 mole of N2O4 produces 2 moles of NO2, so that means it's going to release twice the amount of energy of 1 mole. Great. Why is delta H associated with downward arrow a negative number? Manu.
Because it releases that.
Because when we take two atoms that are apart, we generate a more stable molecule, we release energy. Alright, so for the overall reaction, is energy required?
Yes.
How do we know, Kyle?
Because our input of energy was greater than our output of energy.
Fantastic. To break apart N2O4 requires more energy than is released when we form two NO2s. So that means that overall there's an input of energy. We can see that it's shown in the diagram as well, that one side is higher than the other, and that specifies the relative amount of energy input or released. Is the reaction endothermic or exothermic, Kyle?
Endothermic.
The reaction overall is endothermic. And as we kind of did with the dotted diagram over here, that's how we tell whether the reaction overall is endo or exothermic, is whether the reactants or products is higher. All right, question 6. Based on the information in figure 1, what is delta H in the following reaction? N2O4 generates 2 NO2. What did you guys find? Numerically. Matt?
57.21 kilojoules.
57. That's a pretty small number compared to all these others, right? So when I said earlier that it's putting us in the frame of mind of breaking apart these atoms into into individual atoms, that requires a crap ton of energy because they're really stable together. So we're saying that the actual change of this reaction is relatively small compared to that. 57 kilojoules compared to these almost 2,000 for the other ones. All right, go ahead and draw the energy diagram for question 7a. We have, sketch it really quick. 1 minute, because we're almost out of time. 7a, draw the diagram. Think about which side's higher. And then if you can, put numbers to it, and then go ahead and calculate your delta H. All right, what's on our left side? Someone's having a good day. So our reactants are, where'd I go? The reactants in this case, we're going to draw on our left side. What are reactants? N2 gas and 3 H2s. We're going to draw a line up. What's at the top? 2 moles of N and 6 moles of H gas. So all these are the number of moles. What's delta H for that left side? Did anyone figure that out yet? So we got to figure out how much energy is absorbed when we break apart 1 and 2. How much is that?
Negative 945.48.
Okay. And then how much per hydrogen?
435.3.
So delta H for that reaction, is it going to be positive or negative on the left side? It's going to be positive because we're breaking all those bonds. And did anyone figure out what that number is? Say again? 2,000? On the left side. While Josh is doing that, on the right side, we're going to draw a line for our products. What are our products? 2 moles of NH3. And then the question is that side higher or lower than the other? What is delta H on that side?
2,350.9.
2,350.9.
2,250.9.
And is that a positive or negative?
I'm sorry, I was doing this side.
Oh, you're doing the left side. 2,250.9 kilojoules.
Yeah, and on the right is 2343.52.
2343.9 kilojoules. So should this line be higher or lower than should the products line be higher or lower than the reactants? All right. So I'm going to have to erase that line. I'm going to have to redraw that line lower down because that delta H is greater. Is that a positive or negative delta H on the right side, by the way? We should have a negative delta H there on the right side because those atoms are combining to form the product of two NH3s. So what's the overall change in delta H for this reaction? Can we calculate that for over time by a decent amount? Can you guys calculate delta H for the reaction? So we look at what the overall change is in delta H, and that's delta H for the reaction. What if the reaction went the other way? What would delta H be? So we have, you said negative 93 point something kilojoules. Is that per mole of NH3? Negative 93 kilojoules per 2 moles of product are formed. Or per 3 moles of H2 and 1 mole of N2. That amount is based on these quantities. So if you know exactly how many moles of product, you know have a conversion factor. If we go the opposite direction, what's going to happen to our delta H? So if we're going to the left, delta H is positive. If we're going to the right, delta H is negative. All right, you guys have a homework for this weekend. It is kind of looking at some of this kind of stuff. I highly advise you to work ahead a little bit in this packet, and that might help kind of frame some things. Have a good weekend. I will see you guys on Monday.